Okay, this is going to be the last video on calculating lattice enthalpies by the Born-Haber cycle. I'm going to just give a couple of common pitfalls. Okay, now I suppose the first one I want to say is when you've got things like magnesium chloride, yeah, you've got to remember there are two chloride ions, so that means you need to do 2 times delta H at, and you need to do 2 times electron affinity for the chlorine. Okay, that's fairly obvious. What can be a bit more off-putting is this. Now, delta H at, remember the definition of it. It's the enthalpy change when you form 1 mole of gaseous ions from the element in the standard state. Okay, so, and we have to be things like sodium and so on, that's not too much of a problem. We have to be careful with diatomic things. So i.e., when we're diatomic things, it's the enthalpy change for a half Cl2 gas going to Cl gas. It's not Cl2 gas going to 2Cl gas. It's not that. That's 2 times. That was actually 2 times delta H at, isn't it? But this this is also what we're doing there. We are breaking 1 mole of bonds of Cl bonds. Okay, you break 1 mole of Cl bonds, you actually make 2 moles of chlorine atoms, don't you? Okay, so from that we can see there that 2 times delta H at for chlorine is equal to the bond enthalpy. It'll be dissociation because you're breaking the bond rather than formation of the Cl bond. And if you look at that up in a data book, you'll see this is delta H at for chlorine is 121 kilojoules per mole, and the bond enthalpy is 242 kilojoules per mole. And you have to be careful because sometimes in the question they will give you the data as, sometimes the data they're given is delta H at for chlorine, but sometimes they don't give you that. The data they give you is the bond enthalpy of the Cl bond. So you have to look carefully which data they give you and then decide what you're going to do with it. Multiply it by 2, do nothing with it, divide it by 2, whatever it may be in the case. Yeah. Okay. On one paper, like a couple of years ago, 2017 or something, they actually specifically asked you to explain, as like a 1 or 2 mark questions, why this is the case. Okay. And it's because, like, when you break, if you break 1 mole of bonds, you end up with 2 moles of chlorine atoms, don't you? Okay, right, so that was all I wanted to say there about that. And the next bit of this video is for you to construct your own cycle for, I want you to work out the lattice enthalpy of formation of sodium oxide. Okay, so the data we're going to need for that is we need delta HF of sodium oxide. We need delta H at for sodium. We need delta H at for oxygen. We only need the first ionization energy of sodium because it only forms the Na plus ion, not Na2 plus, obviously. And we need to know the first electron affinity of oxygen and the second electron affinity. Actually, rather than giving you delta H hat from oxygen, I'm not going to give you that. I'm going to give it in a different way. I'm going to give you the bond enthalpy of the oxygen-oxygen double bond. Okay. Now the value for the delta HF for sodium oxide is that's minus 414 kilojoules per mole. Delta H at for sodium, we've had it in a couple of videos before. I think that is, what was it, 108, I believe. 107, positive 107 kilojoules per mole. The first ionization energy of sodium is 496. The first electron affinity of oxygen was minus 141. The second is endothermic, and that's 795. And the bond enthalpy of oxygen is 498 kilojoules per mole. Okay, so construct a Born-Haber cycle for that, and I'll tell you what the right answer is. The right answer is, I've looked it up in the data book, is the lattice enthalpy is is 2478. Okay, formation minus 2478 kilojoules per mole. If you're a few kilojoules out, then that's not a problem. But it should be about that, slightly different values in different data books. So work that one out yourself and see if you get the right answer. And again, with this little twist in the tail here, where we've given bond enthalpy instead of delta H atomization. Don't forget to double a lot of the things there because it's Na2, isn't it, as well? So be careful with that.